Hi all, thank you for being here. Today I'm going to present you the implementation of self-exciting point process models for crime prediction in Bogota and the application of these models for the efficient allocation of police resources. So the model we implemented follows closely the methodology proposed by Mueller in 2011, and we adapted this model for the operative routines of the District Security Office and the Metropolitan Police of Bogota. We used this crime model for 3 specific applications in the city. So the first one was the identification of crime hotspots. Second one was a model for prioritization of the surveillance camera system. And third one, we solved the problem of location allocation of new police stations. So, if you don't know, Colombia is right in the northwest of South America, and Bogota would be right there in almost all of the middle of Colombia. So, as we all know, criminality is one of the biggest challenges megacities have. And for instance, in Bogota, we have what usually happens with crime. That's that crime is spatially concentrated. So, for example, 2% of the street segments of Bogota accounted for all of the crimes and all of the homicides, sorry, and 25% of the crimes that occurred during 2012 and 2015, while these 2% of the street segments only accounted for 10% of the police resources. So there's something that we definitely have to do here in terms of the public policy and in police resources in Bogota. So the model we implemented assumes these 3 points. So first one is that criminality concentrates in specific areas of the city. This we were going to explain by spatial covariates in a kernel density model. For the second part, we have that there's a higher incidence of crime at certain times of the day and days of the week. So for example, you can imagine like Friday nights at like Friday during 10 p.m. and 3 a.m. or something like that. And this we're going to explain with a determined temporal unit in a kernel density model. And lastly, we have that crime spreads from place to place as seismic model activity. So this we're going to explain as aftershock models or replica events. So with these considerations, we estimated the following intensity function. So as you can see, it depends on a spatial coordinates and a determined time unit. So for the first part, we have a functional part that explains the spatio-temporal patterns. So here we want to capture all of the crimes that kind of like randomly or suddenly happens just because of their location and time. And then we have a second functional part that will explain the aftershock patterns. So here we basically want to understand how the crime that occurred in location xk, yk, and time tk spreads along different spatio-temporal locations. The estimation of this intensity function was done with stochastic declustering techniques and kernel density estimation, and we particularly used a Monte Carlo Markov chain to determine whether a crime observation accounted for an aftershock or a background crime. So for our application, since we wanted to adapt it to the operations of the police in Bogota, we considered 6 different shifts in the week. So police in Bogota works by 8-hour slots per day, and they needed to know like how to patrol each locality of Bogota, either in the weekdays or the weekends. So what we did was first divide the week in 6 different times, and then we estimated the kernel mu for the background crimes for each one of these shifts. And then we also estimated the kernel for the aftershock crimes. So with this, the output would be the crime intensity function for each one of the shifts. And then out of this, we were able to determine different hotspots in the city per each shift and locality in Bogota. So right here you can see the heat map for the crime intensity function and the hotspots that we determined for each locality. So the police wanted us to determine 2 hotspots per locality, trying each hotspot to be at least 500 meters away from another hotspot. And this was also the principal input for a model that suggested patrol routes. So to evaluate the predictive capacity of the model, we considered two principal metrics. So the first one was the hit rate. So we wanted just to see the ratio of crimes that would be able to be captured by the hotspots we determined out of all of the crimes that we observed. And we also have the predictive accuracy index that basically wants to see like what would be the increase in the hit rate per each % of area covered in Bogota by the hotspots we determined. So Bogota is divided into 19 localities. So since we had 2 hotspots per locality, we have a total of 38 hotspots, which accounts for the 0.14% of Bogota's area. And by covering this 0.14 area of the city, we are able to capture 3.11% of the crimes and have a percentage accuracy index of 22.29. So this would like basically say that per each % of area covered, we are increasing the hit rate in 22.29%. Definitely, this is a convex function, so if we start like covering more and more area, then this accuracy index would be like lower, but these are like very like promising and nice results for the covering itself with just 38 hotspots in the city. So the second application we did was for the surveillance camera system. So in the past 2 years in Bogota, there has been an increase of the cameras in the surveillance systems from like 2,000 cameras to 5,000 cameras. So the police needed an optimal way of surveilling these cameras. So just like the way to naturally extend our crime intensity model to this camera surveillance was to determine the estimated intensity in each one of the locations where there are cameras located. So right here you could see like our hotspots from the crime intensity function, and right there we have all of the cameras that are installed in Bogota. So it may seem like there are different hotspots. The thing is, what we were doing right there was applying the prioritization for each locality, right? So then if a locality has 100 cameras, then we would just like prioritize which cameras they would have to watch first. Some of the results we had for these applications was that monitoring 10% of the cameras, which would be the 10% of the cameras that have the highest estimated intensity crime, accounts for observing 21.77% of the reported crimes, which is also the 25.01% of the crimes that could actually be seen with the installed cameras in the city. Our last application was the location allocation of new police stations. So with the intensity function that we estimated, we were able to identify vulnerable regions in the city that lacked of having a nearby police station. So with the location allocation problem, we wanted to tackle two kind of objective functions. So the first one was to minimize the response times to the closest police station weighted by the intensity crime. And the second was to cover a minimum rate of estimated crime with the minimum number of new located stations. So you can see right here is an example of 4 new stations that we wanted to allocate in the urban area. We also made it possible for the security office to separate if they wanted to allocate new stations in urban area or rural area, because they would have different objectives. Maybe just like have some police in some area that they know they don't have right now, or like minimize the response times. So some of the results we got here was that allocating 3 new stations in the rural area decreased the mean response times to the closest police station in 20%, which was from 22 minutes to 17 minutes. And for the urban area, allocating 4 new stations would reduce the mean response time from 6.6 minutes to 5.1 minutes. Some of the further work we have is also adding image feature covariates to our self-exciting point process model. So right now we're working with street-level images to add this kind of features to the first functional part that would explain the background crimes. And the second part is addressing the feedback loop. So we want to understand the biases that may appear in crime data while we allocate new police resources in the city. So if you want to talk a bit more about this, I'll be also presenting this in the poster session. Thank you.